Hi, welcome to this video on the formation of coloured ions. And in the background of the slide there you can see a bunch of paint pigments. How do those paint pigments get their colours? Well, they get their colours from transition metal complexes. And we're going to find out in this video how those colours are created. So specifically what we're going to do is what causes the colours of transition metal complexes. We're going to look at that in some detail, and then we're going to realise that colour arises when some of the wavelengths of visible light are absorbed, right, so they don't get to your eye, while remaining wavelengths are transmitted and do get to your eye, right, so that partial absorption of visible light leads to the colours. So we'll look at that in some detail, and lastly we'll see how we can change the colour of these complexes. So various factors like oxidation states, coordination numbers and ligands alter the energy gap, which you don't know about yet, and this leads to the change in colour. Okay, so let's get started with what causes these colours. Let's start off by comparing an iron 2+ ion, and we'll compare that in a straight oxide, not a complex, so no ligands. And we'll compare that to the same iron 2+ ion in a complex. Let's say we've got hexa-aqua complex, so there's 6 water ligands, and it's also got 2+ charge. So we're going to compare those two things and think about the colour as we do so. Okay, so we're going to have a scale, right, and the scale is going to be our energy scale, because we're going to look at the energy of orbitals. So in a normal iron 2+ ion, we have 6 d electrons. And we've got 2 4s electrons and 6 d electrons. You might want to check that out. So in the 3d subshell we have 5 orbitals. Right, let's draw them here. In fact, I'm going to draw them just a bit lower down. So we've got 5 3d orbitals. Like so. And we've got 6 electrons, right? So they fill up orbital by orbital, don't they? 1, 2, 3, 4, 5, and then we get a pair in one of the orbitals, like so. And so that's it normally. Now what we're going to do is we're going to attach these ligands. All right, so we're going to attach our water ligands, and as we do so, what happens is that these 3d orbitals, their energy levels are changed, and they're changed differently. So two of the orbitals are at a higher energy level than the other 3. So there's our 5 orbitals, but now we have an energy gap, right? So we're going to call this here our energy gap. Right, let's fill in our electrons just now. So we've got still got 6 electrons to fill in. So 1, 2, 3, 4, 5, and the 6th one goes in a low energy orbital. Right, so that's what happens, and then what we can do is we can consider a photon of light. So let's give ourselves a red photon, a red energy photon. All right, so I'm going to draw a photon of light like so, and it comes in and it hits this electron here. All right, and it gives its electron, it gives its energy to that electron. All right, so then let's draw it in green. Right, so I'm going to cross it out in green. Right. So if it's been given some energy, and it's been given the energy equivalent to that energy gap, it gets promoted from that first orbital to a higher energy orbital. So there it is there. Okay, so it's been promoted. And that photon of red light there, it's not going to hit your eye, all right, because it's been absorbed by that electron. Okay, so it's the light that does hit your eye is different now compared to the light that would have hit your eye if the complex hadn't been in the way. Okay, so let's get a little bit mathematical now. So this energy gap that we're talking about is this energy gap, right? When we're talking about transition metals and 3D orbitals, that energy gap, that is about the same amount of energy, about the same energy as visible light. You know, visible light is just a form of electromagnetic radiation, i.e. pure energy, right? And it just so happens that the energy gap that's created when a ligand attaches to a transition metal, just so happens that energy gap is the same as visible light energy. And we can get mathematical about this with an equation. So the energy gap, which we can call delta E, the energy gap delta E, right, is given by H, which is Planck's constant, times mu, which is the frequency of the radiation. But it's also true that frequency is equal to the speed of light divided by the wavelength. All right. So what we can see is we can also say is the energy gap is equivalent to Planck's constant times speed of light over wavelength of that radiation. Okay, so you might get a question which gives you, you know, lambda or frequency, and you have to work out the energy gap, or vice versa, that sort of thing. So just to remind you, H is Planck's constant. H is Planck's constant, and that's about 6.63 times 10 to the minus 34 joules seconds. Mu is frequency of the light absorbed. C is the speed of light. I think you know that. It's about 3 times 10 to the 8 meters per second. And lambda is the wavelength of this photon in meters. So there we have it. That is what causes the color of transition metals, because the 3D orbitals shift in energy levels when ligands are attached, and it just so happens that that energy gap that's created by that shift is equivalent to the energy of visible light. Right, so that it gives them their color. Now, before we move on, one more thing, and that is what determines the size of this energy gap. Okay, so we've got an energy gap here, delta E. Right, what determines its size? 4 things. Okay, I'm going to write them up here. Number 1, right, the actual metal ion. Yeah, so the actual metal ion has a say in the energy gap that's created there. Its oxidation number. All right, so here we had Fe2 plus 2 oxidation number. If it was plus 3, it would be a different energy gap. Okay, so we're going to call oxidation number one of the things that determine the size of that. The actual ligand, here we had water, all right, but if it was chloride, for example, that would be a different energy gap created. And the 4th thing would be the coordination number. So the number of coordinate bonds would affect that energy gap as well. Coordination number. So they're the 4 things that determine the energy gap and therefore the actual color. Right. So if that energy gap is bigger, you're going to get a different color compared to whether it was smaller. So now what we're going to do is we're going to take that energy gap concept and we're going to apply it to how we actually see, say, a solution of this complex. Okay, so the bold statement is this. It's so the color arises when some of the wavelengths of light are absorbed, right, by the energy gap we had in the previous slide, while the other wavelengths, which are not the same as the energy gap, so they're not absorbed, and they're transmitted and therefore get to our eyes. Okay, so let's have a picture of a solution. Here we've got a solution of cobalt chloride, okay, and it's blue. So we've got cobalt chloride. We've got 4 ligands, and we've got a -2 charge on the complex. And what we can do is we can shine some white light at it, shall we? So let's put some source of white light here. We're going to approximate white light with 3 colours. Let's say we've got some purple light making up our white light. Okay, so we've got purple. Let's say we've got some green light come along, and we've got some yellow light. All right, so this is I can't see the yellow, so let me draw the yellow as red. Okay, so we've got some red light here. So anyway, that's, as you know, white light is a mixture of all the different colours, and we've got a proxy for our white light here as purple, green, and red light. So and this shines on this complex. So let's switch back to purple, and the purple light shines through here, and its energy, the energy of a purple light photon, is not the same as the energy gap we've got in cobalt chloride, the energy gap that we've got in those d orbitals. So it's going to shine straight through like that. It's going to go pass straight through, not absorbed by any of those electrons in those 3d orbitals. And that's the same for the green light. Okay, that's not the same either, and that's going to go straight through as well. But the yellow light, which we've drawn as red, right, that comes along and gets absorbed. Right, it hits one of those electrons in a lower energy level 3d orbital, right, and the electron grabs it, absorbs that energy, gets promoted into a higher energy level, and that's it. It's got that energy. Okay, so that's where that energy, that photon, stays. Okay, so then when we look at it, let's draw an eyeball to see. Right, so we're now looking at this. So we see white light minus our yellow light, right, and white light minus yellow looks blue. Okay, so that's why this solution looks blue, because we can see everything except the yellow light. And so that's how the energy gap absorbing certain visible light wavelengths leads to the colours of the solutions. And what a little extra point on this topic is the size of the energy gap. Okay, so what you've got on the top there is a whole complete electromagnetic spectrum, right, from low energy radio waves at the right hand side, and you've got gamma rays, which are of course very high energy. Yeah, and visible light here is sort of in between, in the middle of the energy spectrum. And if we expand our visible spectrum so that we can see it, we can see the red light at the right hand side is lower energy by the standards of visible light, and indigo light is our higher energy visible light, visible light. So what we could say then is that if a energy gap is going to absorb red light, all right, so we've got our energy gap here. Let's describe it like that. That's our energy gap. Right, so that's a smaller energy. Right, so that's a smaller gap. Then on the other side, let's pictorially represent the energy gap that would absorb indigo light. Right, so we've got our 2 3D orbitals like so, and we've got our other 3 3D orbitals like so. And as you can see, we have a bigger energy gap. Right, so let's say delta E is bigger. and therefore this energy gap here is the one that would absorb the higher energy light, so our indigo light would not get through, whereas the opposite was true with the red energy. Okay, we mentioned before that various factors affect the size of this energy gap and therefore the color of the complex. Let's just be clear that if we're talking about the color arises from the energy gap. All right, so and what affects the energy gap are not only the metal ion but three other factors as well. Right, so three factors other than the metal ion affect the energy gap, and the energy gap affects the color of the complex. Okay, so let's draw a little energy gap. So here, and let's call our energy gap delta E. So that's the energy gap that we're talking about, and there are three factors. There's number 1, that's going to be number 2, and this is going to be number 3. There are three factors that affect it. I've mentioned them already. One of them was oxidation state. So the oxidation state of the metal ion, and we had Fe2+ on an earlier slide. So let's stick with Fe2+. Let's so if we've got Fe2+ and 6 water ligands, all right, the complex, of course, because water is neutral, it's going to have a 2+ charge overall. Okay, so the color of that is green. All right, so let's get a bit of green color here and draw a little box around that to suggest it's green. And shade it in. Okay, so if instead we had iron 3+, but our control variable is our water ligand, and another control variable is the coordination number. Right, so in this case, the only thing that's changed is the oxidation state of the metal ion. So that's now a 3+ ion complex, and the color of this would be yellow. All right, so let me draw it in this sort of slightly different yellow color. All right, so we've got a change of color from green to yellowish orangey color when we change the oxidation state of the metal ion. So that's the first thing. Second thing is the coordination number. All right, so if we change the coordination number, then we can change the color by means of changing the energy gap. Let's look at an example. We haven't got such a good example in this case, so let's look at copper aqua complex. Right, so we've got water, and we've got 6 water ligands, and it's a 2+ ion. Right, but if we change the coordination number, we actually also have to change the ligand. Right, so we're going to compare this to copper chloride complex. Right, so that's a 2- charge, and the colours of these two are the coordination 6 copper complex is blue, and the coordination 4 complex is yellow again. Okay, so we've got a change of colour. It's not a great example because you can see the ligand has also changed, but in this case that change is down to the coordination number going from 6 to 4. Okay, so the coordination number changes the color, and also the ligand changes the color. The ligand changes the color, so let's look at a cobalt complex this time. So this time we've got cobalt aqua complex with a coordination number of 6. And this is a 2+ ion and 2+ complex. And if we changed our water ligand out, if we substituted out those and we put ammonia in instead, so there's our ammonia. We've got a coordination number of 6 still, so that's a good control variable. So the only thing that's changed here is the actual ligand. They're both coordination number 6, and cobalt was still 2+. So lastly, let's just check that we've covered off all our objectives. And firstly, what causes the colours? Well, we can summarize that for our memory purposes by drawing a little energy gap between the 3D orbitals, and that energy gap being equivalent to the energy in visible light. Okay, so that was the first thing, and colour rises when some of the wavelengths of visible light are absorbed, whilst others passing through and hitting our eyeballs. Right, so that determines the colour, and also identifies the transition metal. And lastly, we've looked at the 3 factors that change the colour, that being oxidation state, coordination number, and ligand. They alter the energy gap and therefore the colour. Hopefully that's been clear.